All right, so today we're going to be taking a closer look at the logarithmic function and looking at some applications of the logarithm. So first of all, in example 1, we're just asked to graph y equals the log of x and y equals 10 to the x. All right, well, let's do that then. Let's put in some values for x. Graphing 10 to the x, that's not too bad. We just put in, I just chose some values here. On either side of 0, so -3 through +3. And so if we take 10 to the -3rd, that's basically 1 over 1,000. So 1/1000th looks like 0.001. And then 10 to the -2, that's 1 over 100, which is 0.01. 10 to the -1, that's 1/10, 0.1. And then the 10 to the 0 is just 1. And of course, then 10 to the 1, 10 to the 2 is 100, and 10 to the 3rd is 1,000. Okay, so that's easy enough. Let's see if we can graph some of those points. Now, obviously, I don't have, some of these points I can't even graph because, my scale only goes up to 10. So I won't be able to graph 10 to the 2nd power or 10 to the 3rd power. And it's going to be difficult to graph 1/1000th. It's pretty small. So let's just graph what we can. Now, probably the easiest thing is when x equals 0, y equals 1. So let's graph that point right here. And then when x equals -1, we have 1/10. Now that's pretty small, so it's somewhere down in here. That's probably even too high. And then 10 to the first power is 10, so that's just right up here. All right, so that's pretty much all we can graph realistically. So let's just connect the dots and see what that graph looks like. All right, so I've just connected the dots there, and you can see what you would expect. It's an exponential function. So it grows really fast as x gets larger. It's just growing really fast, right? So let's take a look at the log of x. Now remember, the log is the exponent, all right? So it's the inverse of 10 to the x. So now notice I haven't actually listed any x values to choose. We want to choose probably, I could choose 0, 1, 2, 3, like I did in the previous example, but it's much easier to choose values that are easy to take the logarithm of. And of course, those would be powers of 10 because the log is the exponent. And so if I have a power of 10, all I have to do is to find the log of it is just take the exponent. So why don't we do this? Why don't we take 10 to the -3rd and 10 to the -2 and 10 to the -1 and 10 to the 0 and 10 to the 10 to the 1, 10 to the 2nd power, and 10 to the 3rd power. So those are just easy x values to take the logarithm of. And if you notice, they happen to be the output of the exponential function, right? So, and you probably learned in 108 that that when you have a function and its inverse, the input becomes the output and the output becomes the input. So it makes sense that we would use the output of 10 to the x as the input to the log to get nice values out, right? And so you can see if we do if we take the log of 1/1000th, right, that's just -3. 1/100th is -2. 1/10th would be -1. The log of 1 is 0, right? Because 10 to the 0 is 1. And then the log of 10 would be 1. The log of 100 would be 2. And log of 1,000 would be 3. So you can see we've just basically swapped the inputs and outputs, right? So so let's graph what that looks like. Again, I can't graph all of those points, but I'm just going to graph the ones that are easy to graph. So obviously 1, 0, that's right there. 10, 1, all right, that's right there. And probably the other one would probably be maybe 1/10 at -1. So let's put that one, I don't know, somewhere around there. All right, so now we just need to connect the dots. Okay, so I've connected the dots. So we should probably label these. This is y equals log of x, and this one here is y equals 10 to the x. Okay. Now we also learned about the natural log. Now this question doesn't ask us to graph the a graph of e to the x or the log of x, but just for the sake of completeness, let's just compare the two. Now when x is equal to 0, e to the 0 is 1, so they both share this point here, this e to the x function, okay? And e is like 2.7 something, so at 1, you're going to get about 2.7, so let's say about there. And then e squared is somewhere around 7 point something, so let's do, what is it? Somewhere about there, okay? So this is what e to the x looks like. I could draw that in as well. All right, so there's my graph of, or my sketch of a graph. It's very sketchy. Graph of e to the x. You could say it doesn't quite grow as fast because e is a smaller number than 10, of course. So, so let's take a look at what's the natural log look like. All right. So again, they're going to share a point at when natural log of 1 is 0. Natural log of so that's because e to the 0 is 1, and then we can sketch in the rest here. All right. So there I've sketched in what the natural log looks like. Okay. That gives you an idea of what they look like. Now let's take a look at some properties of these two types of functions. I'm just going to look at 10 to the x and a log of x. So what is the domain? So remember that the domain is the set of all the input values, all the x values. So if you look at the domain, we're just let's just look at the 10 to the x. Really, we can put in any number for x, and we can raise 10 to that power. There's no limit. I can put any negative number in, any positive number, anything. So the domain is really all real numbers. So I'm just going to put in here all real numbers. Okay, and the same holds for e to the x as well. But in interval notation, we can denote that as negative infinity to infinity. All right. Now, what about the range? The range is all of the output values, all of the possible output values. Well, 10 is a positive number, and if we raise if we raise 10 to any power, then we always get a positive number. So the range will be only the positive values of y, right? Y can only be positive. So if we wanted to put the range in interval notation, we could write it as 0 to infinity. Okay, because it's never going to be negative, right? Any power of 10 is always going to be a positive number. How about the rate of change of the function? Okay, now when I talk about the rate of change, I'm really talking about the slope. What does the slope of the function look like, right? Because we're looking at the change in y over the change in x. How is y changing with x? All right, well, let's just take a look at our 10 to the x function. And if I take let me see, I'm going to use a different color here. If I take a point down here, like say down here, and I look at the tangent line at that point, you can see it's, fairly shallow, right? So that would be a low slope, but it is positive, right? It's a positive slope, but it's fairly small, right? And if you look at a point up here, let's say I wanted to look at the tangent line to a point at a point up here. Kind of hard to draw in here, but you can see that it's much steeper. Okay, but it's still positive. And no matter where you choose a point along here, you're going to get a positive slope, right? Now this looks like it's pretty close to 0 down here, but you can also see too the slope just keeps getting steeper as well as you go up. So what can we say about the slope, the rate of change of the function? Well, we know that it's always positive, okay? Positive, right? The slope is always positive, which means that the function is increasing, right? So the function is increasing. Always. Okay. How about the rate of change of the slope? All right, so we were looking at the rate of change of the function. Now we want to look at how the slope is changing. All right, so this is what you would be looking at with your second derivative, right? So how is the slope changing? Well, we already kind of talked about that. You know, it's as x gets larger and larger, the slope gets steeper and steeper, so it becomes larger, right? So the rate of change of the slope is also positive, right? Because the slopes are increasing. So positive. So we have a positive rate of change of the slope, which is a positive second derivative. And what does that mean? That means it's concave up. So our graph is concave up. Okay, concave up and increasing. The function itself is concave up and increasing. All right, horizontal asymptote. If you take a look at our function of 10 to the x, obviously we already said that it has to be, it always is positive, right? And we actually have an asymptote at y equals 0, right? Because it can never go below the x-axis, which is the y equals 0 line. So our asymptote is y equals 0. Are there any vertical asymptotes? No, we already said the domain is all real numbers, and so there's no vertical asymptotes. It kind of looks like, you know, it's great, it's increasing pretty fast, but it actually can increase without limits. So so there are no vertical asymptotes, none. All right, so now let's take a look at the log function and see how it compares. Y equals log of x. All right, so let's look at the domain of the function. All right, so domain are all the possible x values. Now, if you try to take the log of 0, say, you're asking, well, what power of 10 gives me 0? And that's not going to work. Okay, so also a negative number. If I try to take the log of a negative number, what power of 10 gives me a negative number? No, it doesn't work, right? So x has to be greater than 0, all right? Or our domain is 0 to infinity. Okay, I can put in as big a value as I want because I can find a power of 10 that would give me any positive number, but anything negative or 0, no, it's not going to work. How about the range? The range of the log function. Well, so the range are all the possible output values, so all the possible y values. And actually, we can have any y value. So the range is just all real numbers. All real numbers. And if you want to put it in interval notation, it's minus infinity to infinity. Okay. I don't know if you're familiar with interval notation. I know it does get used in your book a little bit, so I'm just going to go ahead and throw it in so it's not totally familiar to you when you run into it. Okay, so now what is the rate of change of the function? Well, you can see, we can look at the rate of change is the slope. So if let's go back to the blue, you know, if I look at the slope at any given point, let's say I look at like point like this, well, our slope would look like that. It's positive, right? If I look at a point, let's say I look at this point, again, it's positive. It's kind of hard to draw it in there. It's a little bit shallower. Now down here, it's definitely positive, and it's very steep. So, so what is the rate of change of the function? Well, the slope is always positive, just like positive, right? Just like our 10 to the x, it's always positive, which means it's an increasing function. Okay, it's increasing everywhere. All right, how about the rate of change of the slope? Okay, so now we're looking at how the slope is changing, not the function itself, but how the slope is changing. And you can see when we take values that are sort of close to 0, you know, small values less than 1, we get a fairly steep slope. And then as x gets larger, then our slopes become more and more shallow. Okay, so in this case, the rate of change of the slope is becoming less, right? It's becoming less positive. So we have a negative negative rate of change of the slope, right? Which means the second derivative would be negative. We would expect if we could take the second derivative of the log of x, which we haven't learned how to do yet, but it would be negative value. And so it's concave down. Concave down. Okay. All right. Now, horizontal asymptote. So horizontal. All right, horizontal would be parallel to the x-axis, and there really aren't. We already said that the domain, the range is all real numbers, so there is no horizontal asymptote, so there is none. And the vertical asymptote, well, we already said that when we looked at the domain, we said that x has to be greater than 0. And we can see that we do have, as we approach 0 from the right-hand side, we just get closer and closer to 0, but we never actually get there. So there is an asymptote at x equals 0. Okay. Now you notice, again, these are inverses of each other. These functions, 10 to the x and log of x, are inverses of each other. And you can see how the domain and range sort of just swap in a way, right? Or at least the limits on the domain and range swap, okay? You can see that the horizontal asymptote becomes a vertical asymptote when you swap things around. And there is no vertical asymptote. There's no vertical asymptote for 10 to the x, so there's no horizontal asymptote for log of x. All right? All right, so that gives you an in-depth look at the graphs of the functions, and I'll meet you for the next video.